right, today we're going to begin our work on lesson 6.4, which is solving absolute value inequalities. Okay, so we've solved absolute value equations and we've solved inequalities, and now we're going to put these two ideas together and show you what that all entails. There's a little bit to it, and we'll see exactly how we have to interpret these and how we get the work done here. All right, first of all, let's take a look at a basic example here, and we're going to look at the less than or the less than or equal to symbol when it's involved in absolute value. Okay. So when you look at the big picture here, okay, remember absolute value is the distance a number is from zero. So what we're saying is we want to find all the numbers whose distance from zero is less than 3 units. Okay. All numbers whose distance from zero is less than 3 units. If you look at that on a graph, okay, so 3 units from zero obviously is 3 and -3. Okay, we want the answer to our x values here to be numbers that are less than 3 units from zero. So if you look at it graphically, it would look like this. Okay, because obviously from 0 to 3, all the numbers in here are less than 3 units from zero. 0 to -3, all the numbers in here are less than 3 units from zero. Okay, this represents this graph a compound inequality. Okay, that compound inequality could be described as this. This graph represents numbers that are less than 3 and x values that are greater than -3. Remember, greater than -3 is to the right of -3, less than 3 is to the left of 3, and then and means the only numbers that will count in that is the numbers that fit both descriptions. All right. So whenever we have a less than with absolute value, we're going to use the word and we're going to rewrite it as two different absolute values. Okay. So this absolute value of x less than 3 is the same as this. Now, notice I don't have absolute value in here more because these two statements take the place of the absolute value. Okay. And we call them cases. So that would be case one. This would be case two. So what's going to happen with our absolute value inequalities is we're going to have to write two cases and then solve those two cases. Okay. So now, okay, we know that the solution is the intersection of their graphs. If you look at the greater than or equal to symbol, so let's look at this. Now we're saying we want to find numbers or values for x that are greater than 3 units. Remember, absolute value means distance from zero. So we're looking for numbers whose distance from zero is more than 3 units. So again, look at your number line. And if I was to graph numbers that are more than 3 units from zero, I would make this graph, right? Because obviously from 0 to 3, that's 3 units from zero. The numbers that are more than 3 units from zero are the ones that go away out to the right from 3. And because absolute value is a distance, right? -3 is 3 units from zero. And the numbers to the left here are numbers that are more than 3 units from zero. Okay. Remember, absolute value is a distance and it's non-negative. So we have to look at it this way. Now, if you were to write a inequality for this graph, you would write this. We're looking up here at numbers that are greater than 3 or x values that are less than -3. That equal to should not be there. Okay. So there's my two cases. So when it's a greater than symbol, okay, you're going to write, obviously, we're looking for values of x that are greater than 3 or values of x that are less than -3. Okay, remember the solution here with an or is the union of the graphs. Okay, all right, let's look at a couple of these done in examples that you're going to see tonight. So this one says solve the absolute value of v is less than 2 and then graph the solution set. Okay, all right, less than 2 means it's less than 2 units from zero. When it's less than, we're using and. Okay, and the way we do this is we're going to take this original inequality that involves absolute value. We're going to rewrite it with its two cases. The first case is when you just write v is less than 2, as is. And the second case, we're going to change inequality and we're going to change this to its opposite. So v is less than 2 and v is greater than -2. Okay. So again, what these this statement is describing are all the possible numbers that I could put in place of V and make this true. Okay. So if I make a graph of this, and is the intersection. So V is less than 2 would be this way, right? Open circle on 2 to the left. V is greater than -2, be an open circle on -2 and go to the right. And then the intersection is here. Now, if you take any one of the shaded in, the where we shade in our number line, any number values in here, put it in place of V, it's going to make it true. Put in -1. Absolute value of -1 is 1. 1 is less than 2. True. Put in +1. Absolute value of 1 is 1. Less than 2. True. Put in -1.5 or +1.5, -2.9. Anything in here, when you substitute it in place of V and then take its absolute value, is 2 units, is less than 2 units from zero. All right. So this graph is the answer of numbers that I can put in here and make it true. All right. Another one here. Oh, and by the way, this is set builder notation. I think we've talked about it. I just want to review it with you. When we write set builder notation, we got to write it as a set, which means we're going to use this set symbol concept here. So it's going to be the set of the variable V. This means such that. Uh, and remember, we can write it when we have an and, we can write it like this, a compound inequality. So the way I would read this is I start in the middle and say V is greater than -2 and V is less than 2, which is what the graph is. But remember, when we have and, we can write it as a compound like this. Okay, let's look at another one here. X is greater than or equal to 5. Okay, greater than means more than 5 units from 0. So we'll be shading out on each side. So that's going to be an or. So the way we write it is we're going to rewrite it as the first statement without the absolute value. X is greater than or equal to 5, or, and then we're going to write X is less than or equal to -5. Switch the inequality, make that number its opposite. Okay. Now, if I graph it, it looks like this. So X is greater than 5 or equal to, so it's solid, shade to the right, or X is less than or equal to -5, shade to the left. And what we're saying here is any number in the shaded part of the number line, if I put it in here, is going to make it true. So pick 9. Absolute value of 9 is 9. 9 is greater than or equal to 5. True. Pick -6. -6. Absolute value of -6 is 6. 6 is greater than or equal to 5. True. Okay. All of the numbers going from to the left here to infinity, all of the numbers going to the right to positive infinity, those are all numbers that will make this true. All the numbers in here will make it false. Okay. If I had to write it as in set builder notation, I'd write X such that, and then I'd just write this statement. We don't have a combination here, to write this. We just write it as is. So X is greater than or equal to 5, or X is less than or equal to -5. All right. Now, next style of question looks like this. Okay, it's a little bit more complicated. You can see I have absolute value y plus 14 less than or equal to 27. So we got this addition of 14 to the left side of the inequality, or to my inequality. All right. And then the directions are going to say this. If all real numbers are the solution, then click all reals. If there's no solution, click no solution. Okay, now, so let's go to work on this one. There's one thing we got to do to start with. Before we write our two cases, which we always have to do when we have an absolute value with an inequality, we have to do it with an equation too. If you remember, we got to write two cases. Before we write our two cases, we have to have the absolute value isolated. So I have to have this isolated before I write two cases. Okay, so how do I isolate this absolute value of y if it has 14 added to it? We subtract 14 from each side. Okay, so subtract 14 from each side. I wind up with the absolute value of y is less than or equal to 13. Now that it's isolated, I can write my two cases. Less than or equal to 13. What conjunction and or do we use with this? Well, it's and. Remember, less than 13 is less than 13 units from 0. And I'm going to write my two cases. Y is less than or equal to 13 and y is greater than or equal to -13. Switch the inequality, switch that to its opposite. Remember what the number line will look like. Okay. Oops, I didn't make a number line there. I'm sorry. It didn't say I had to graph it. So I just rewrote it in set builder notation. y such that, and again, I read these from the middle out. So y is greater than or equal to negative 13 and y is less than or equal to 13. Any number in that range, when you put it in place of y, will make it true. Okay, that's what we're trying to do, is find all the numbers that will make this true. Okay, look at another one here. Absolute value of x minus 5 is less than negative 11. Same set of directions. Okay, same starting point here. Before I can write two cases, and you have to write two cases when you have a compound inequality here with absolute value. Before I can write two cases, I got to isolate this absolute value of x. I want this by itself first. So we're gonna add 5 to both sides. Absolute value of x is less than negative 6. Now, at this point, we need to stop and think about what this says. We're saying that the distance a number is from 0 has to be less than negative 6. To be less than negative 6, you have to be a negative number. Is the absolute value of any number ever going to be negative? No, never. Absolute value is a distance. Distance is always positive or 0. All right. So as you analyze this, since the absolute value of x will always equal a number greater than or equal to 0, so it's got to be a positive number, this statement can never be true. Never will a positive number be less than negative 6. So it doesn't matter what number you put in here, this can never be true. So the answer is there's no solution. It's the empty set. So once I have my absolute value isolated, you need to take a look at this number. And we need to look at what this means. Less than negative 6 can't happen. All right. So this is a case you got to keep an eye out for. Again, these instructions up here, this is why it's there. Okay. All right. Let's look at another one here. Absolute value of g minus 23 is less than or equal to negative 12. All right. Now, one thing you can't do is jump to conclusions, say, whoa, we got a negative number over here, so this one doesn't work. No, you always got to go by the process. The process is isolate absolute value first before you analyze and make your determination. Okay. So how would I isolate the absolute value of g? Well, I'd have to add 23 to both sides. So the absolute value of g is less than or equal to 11. That's a positive number, so we can do this. Okay. So less than or equal to 11, that is an and. So it's going to be g is less than or equal to 11 and g is greater than or equal to negative 11. Okay. And that works, obviously, right? So I could write it in set builder notation this way. Again, read it inside out. G is greater than or equal to negative 11 and g is less than or equal to 11. The numbers in this group, if you plug them in place of g, it will make this true. Okay. That's the whole objective. And then this example here, absolute value of k plus 7 is greater than 3. Same set of instructions. Okay, first rule always isolate absolute value before you rewrite your two cases. So the first thing I have to do is subtract 7 from both sides. And I get an absolute value of k is greater than negative 4. Okay, now whenever there's a negative number over here, we got to look at the situation. All right, absolute values of any number, whether it's positive or negative, is going to be a positive number or 0. Okay. Every positive number or 0 is going to be greater than negative 4. Okay. All positive numbers and 0 are always greater than negative 4. So what this means is this statement is always going to be true, no matter what number you put in place of k. So here's where we would say all real numbers. I can put any number I want in place of k, and this is always going to be true because the absolute value of k is always positive, and a positive is always bigger than a negative. Okay. So again, once we've isolated absolute value, now we analyze before we write our two cases. Okay. Last kind of example here. They just give us a little bit more work to do here inside our absolute value. And I just want to show you how to write these so that we're careful with it. All right. Now, first step is always to isolate absolute value, right? Well, it's isolated. The absolute value of w minus 3, this quantity is all inside absolute value, and that's over here by itself on the left. Okay, so we're ready to write two cases. Okay, what does less than mean? What conjunction? Less than is and. So we're going to say w minus 3 is less than 3 and w minus 3, same quantity, w minus 3 has got to be greater than negative 3. Okay, you always drop the absolute value, write the first case as is, and the second case is the same quantity inside absolute value. Change inequality, make that its opposite, and it'll set it up for you. Okay. All right. Now, I have to solve these, right? You can't just leave it as is. So let's solve this. So how do we do it? We add 3 to both sides. And I get W is less than 6. Over here, add 3 to both sides. W is greater than 0. And remember, our conjunction is and. So if I wrote it as a compound statement, I'd write it like this. Again, inside out, W is greater than 0 and W is less than 6. That's a compound inequality with and as its conjunction. If you graph it, they did say to graph it, it would look like this. So open circle on 0, open circle on 6, fill in the number line between. This filled in area are my answers. So I can take any one of the numbers in this region here, put them in place of W, and it makes this true. Any number outside of it will make it false. Okay. But I just want to show you how to rewrite this. I think I got one more here. All right. So W minus 4, absolute value is going to be greater than or equal to 6. So here's my statement. Is absolute value isolated? Yes, it is. It's over here by itself. So I'm ready to write the 2 cases. Greater than is or. So we're going to write our 2 cases. Okay. Y minus 4 is greater than or equal to 6. Or y minus 4 is less than or equal to negative 6. Okay. 2 cases. Notice that these 2 cases don't have absolute value in them. I rewrite them both so I can see them. And now I solve them. Okay. Add 4. Y is greater than or equal to 10. Add 4. Y is less than or equal to negative 2. Remember, my conjunction is or. Now it said graph it, right? So if I graph it, it looks like this. Greater than or equal to 10. Less than or equal to negative 2. There's my graph. All the numbers in the shaded areas will make this true if I put them in here. Any number in between these two will make it false because it's not part of the answer group. Okay. I guess I'd have another one. All right. So this doesn't change how we do it, right? Uh, we go through the same process. There's my inequality given. It has absolute value in it. So we're going to need 2 cases. Okay. We're greater than 5. So greater than means you're going to use or. So write your 2 cases. Okay. 5u minus 15 greater than or equal to 5. That's the first without absolute value. And then switch inequality and make the 5 negative. Rewrite it. 5u minus 15 less than or equal to negative 5. Okay. Solve them both. Add 15. 5u greater than or equal to 20. Divide by 5. U is greater than or equal to 4. Over here, add 15. Divide by 5. U is less than or equal to 2. My conjunction was or. It said graph it, right? So it would look like this. Greater than or equal to. No, you know what? It shouldn't have been greater than or equal to. That's where my graph doesn't match it. I just had greater to here, and I made it greater than or equal to. That's just a mistake on my part. These should all be greater than. These should all be less thans, and we would not have a closed circle be open. Okay? But all the numbers here are answers. All the numbers here are answers. So none of that changes. Last one. Again, process. Absolute value, is it isolated? Yes, it's over here on the left by itself. We got less than or equal to 6. So less than or equal to 6 means we're going to write and. 2 cases, 6d plus 12 is less than or equal to 6. And 6d plus 12 is greater than or equal to negative 6. This will give me my 2 cases. And then we solve them. Subtract 12. 6d is less than or equal to negative 6. Divide by 6. D is less than or equal to negative 1. Over here, subtract 12. 60 is greater than or equal to negative 18. Divide each side by 6 to get the coefficient of D to be a 1. And I got D is greater than or equal to negative 3. The conjunction is and. Okay, so I can look at it as this compound, statement. D is greater than or equal to negative 3 and D is less than or equal to negative 1. And when I graph it, it looks like this. Okay. And all the numbers in here are possible answers that I could put in place of D. These are the only possible answers, right? None of the numbers out here, over here will make that true. Just those. So those are the kind of problems you're going to work on tonight with our concept of absolute value inequalities. It blends the two ideas together that we've already worked on. Okay. So make sure you have paper pencil out. You're writing these down and showing the work for how to do it. And it's going to help you tremendously to write things out. Okay. All right. I'll let you have at it.